Welcome to the quantum seminar, everybody. It's the second to last seminar. Next week is the last seminar. Today we are super happy to have Professor Kawarada from Waseda University in Tokyo, Japan. Professor Kawarada, he is actually a known face, let's say, in Waseda University, because that's also where he got his master's. And then after a brief stint in industry, he worked at Hitachi actually for 2 years. He graduated with a PhD also in Waseda University. Then an assistant professor at Osaka University and back to Waseda University as an associate professor. And then from 95, he was as a full professor at the School of Science and Engineering. I think in 95 he also had a brief visit to Germany I believe in Freiburg for a year, working in the Fraunhofer Institute there. So additionally, he is the director of research organization for nanoscience and nanotechnology. And overall, we are super happy to have you here, and we are looking forward to your talk about diamond superconductivity for new SQUID and quantum applications. So, floor is yours.
Okay. Vielen Dank für
Einladung.
Thank you very much for the Einladung. And,
we could have it in German. Perfect.
Yeah. Nein. So, well, this is the first time I go to the Mainz, because I always see your city from, railways, but only from the railway. So the Rhine River is very good, and but unfortunately I didn't. This is the first time I visit. so thank you very much for the invitations, and this is one of my pleasure to talk about the diamond superconductivity in front of the people who are specialized in atomic or quantum physics. So I think my area of superconductivity is relatively application-oriented, and also my specialty is to do device research to make a field effect transistor or high frequency field effect transistor, high voltage, and also making some sensors. And so the diamond is right now very famous for the nitrogen vacancy center, but also another topic is the superconductivity device, because diamond is, as you know, very hard material, the environmentally very strong. So in high temperature, or because temperature is not so high in the point of the superconductivity, but it's very robust material. So I think it's one of the application why they're thinking it's the SQUID, which is very hard. I'm quite against the friction of so this is one of the small SQUID microscopy we are aiming to produce. And also another quantum application we can imagine is that we are making a SQUID in a small size, and then we get qubit, of course, but also we are combined with our field effect transistor technology. And later I'm going to show you some of the examples, but I think the source drain means the superconducting regions are very close to and then we could get proximity effect, or those Cooper pairs could be controlled by the field effect that we hope. But this is what we want. But unfortunately, this is not realized, but we are hoping to make something new from the point of quantum application. So let's start. So this is a semiconductor diamond, which we're going to use. And the semiconductor diamond comes from its doping. The doping boron. So if you know this diamond, which is we call blue diamond, and blue diamond is famous, but this special hope diamond is a little bit tragic stories they have. But anyway, it in the Smithsonian Museum in Washington, D.C., maybe this is a historical, natural history museum, because the Smithsonian Museum, there's a lot of museums, but one of the museum in the array of the museum. So the boron inside diamond shows this is the acceptor. Boron is acceptor in the semiconductor properties. So it shows relatively, in our sense, little bit deep acceptor, what means the activator energy is very large. So the room temperature, we cannot expect conducting, but a little bit high temperature, like 300 to 400, those acceptor, that means valence electrons activated into the impurity levels and then shows p-type semiconductor. But when we introduced boron, like that we call the 10 times 10 to the 22nd or that much, then we get very conductive diamond superconductor, sorry, and the conducting layer we can observe. So this is what happens in the case of boron, because it is a substitution site, it occupied. And well, I said 10 to the 22nd means it's a more than 5%, nearly 10% of boron substitute the carbon rights, then it makes degenerate semiconductor and shows superconductivity. That's what we are using. And those diamond I think it's better to explain what the diamond we can make, because we started diamond research on the synthesis of diamond for the problem phase. So we are using methane and oxygen, CO2 and hydrogens to form the diamond. And we use the plasma-assisted chemical vapor deposition technique, where the methane and hydrogen are decomposed into the atmosphere. But this atmosphere is relatively low pressure, because it's less than atmospheric pressure. But for the plasma-assisted CVD, which is normally used of the semiconductor industry, well, I think from that point of view, this plasma is relatively high pressure, and it's the 1/10 of atmospheric pressure. So the plasma is very, dense and a very hot plasma we're using. And then the diamond could be made from that. Well, just we are showing the conditions. So the carbon, hydrogen, oxidants, and we have a diamond stable phase in this phase diagram of the carbon, hydrogen, oxidants. So one point, or the one lines we can have here is a CO line, where we can get carbon and oxidants 1-to-1 ratio. So we get relatively high quality of the crystal we get. So firstly, we use the carbon monoxide, but carbon monoxide, as you know, the very toxic gas. So we're using methane and CO2, which is a mixed gas, and then we get carbon, and the remaining or the byproduct is water. So this, just a simple chemical reaction process is very simple, and I like this one very much because of the methane and the CO2 is a greenhouse gas, and we get diamond from that. So diamond solidify those greenhouse gases. Okay, so maybe people like to know how much does it cost. So the cost of single crystal diamond wafer, or like this, the size is very, both the semiconductor industry people always ask me, okay, your device is good, but how much does it cost? So, well, we can answer the questions. And then, well, 1 square centimeter is $9, and 2 inch is 2 inch. It is a 5 centimeter diameter. It's about $200. So this cost is just raw cost, means just include manpower, electric power, and gas, and polishing process, and recycling of the substrate, because recycling substrate is also very important to get diamond wafer. So the most cost is its reactor. So if operator's cost is very high, still high. The reason is the operator's cost we can reduce, but the most bad things always happens is the diamond people like jewelry better than superconductor or semiconductor applications. So the plasma reactor normally used for the gem industry or the jewelry industry. So right now, people making jewelry from this process, and the reactor is still very expensive. Of course, we are using self-made CVD machines, and so in that sense, we are making diamond very cheaply. So people think diamond is expensive, but it's just carbon. So how do you get the diamond from the gas phase? It's very simply we can explain from this view graph, where the diamond surface is covered by hydrogen. The hydrogen is very important to stabilize diamond in a surface point of view, because it stabilizes sp3 bond. Okay, so it's just a pull the graphite phase. So without hydrogen, what happens in the surface at high temperature, the surface covered by graphene. Okay, so that's another point. The people like graphene, oh, why don't we use a diamond surface? But anyway, without hydrogen, the surface become gravitations. Then hydrogen, it pull the diamond bond. Okay, so to make a sp3 stable. So some part, also how to get the layers of the diamond, we use the methane in this case, and the methane is decomposed into metallurgical, which is CH3. It's a planar structure, and then it shows like that. And some part hydrogen terminate diamonds points are replaced by metallurgical, and then get one monolayer or one layer carbon phase. So, and this is one of the examples that we took pictures more than 20 years ago. And at that time, I was very interested in the surface science, and surface properties of diamond is also very interesting. And we measure the atomic scale diamond, how to terminate by hydrogens. So these 5 points correspond to the hydrogens on the surface. But other disordered point, we thought this is a defect of surface. But I think we take many pictures. That what we found that is the remaining of those metal or the hydrocarbon layers, which are going to start the new layer. So this is not defect, but I think this is a precursor or some of the diamond island to get another layer. And this is the surface is a very interesting point of view, because this is it's already p-type nature. And I didn't explain about the p-type nature of diamond surface, but STS, the scanning under microscopy, so under spectroscopy shows that it is a p-type nature, and the surface is two-dimensional whole gas we observe. But this is another story, so we don't explain these things today. But this is another point, another interesting point of diamond. So now we are studying superconductor diamond and many properties. So if you have any questions, please make questions during my talk, because it is more efficient to explain, because I don't know what kind of interest you have, or what, I don't know what is your background. So I think it's better to ask me if you want. So anyway, this is a schematic, this is experimental biograph of diamond conductivity. It is resistivity as a function of the boron concentration, which is made by the French group. And the beginning, well, just before the year 2000, it's a relatively classical data, but it shows that in the semiconductor people, this is contents of the impurity levels, and I said the superconductivity start from 3 times 10 to the 20s per square centimeter, as a cubic centimeter, and this is less than 1% of the 0.1%, and then semiconductor property change to superconductor in these regions. So this is very unique, and from the point of semiconductor concept, we can say this is a degenerated states of the impurity levels, and it shows the Fermi surface become round to orbital more anisotropic structures. But anyway, this is these areas we can get superconductivity. And the boron doping is very efficient to get superconductivity. And there is some other, well, phases, but I think today we're just focusing on these regions. So the first superconductivity has been observed by Russian group in 2000, I think, 4 or 5. Okay, 2004, and the published in Nature. And at that time, I was not so much interested in the superconductivity because well, I'm a semiconductor scientist. So one of the people who are doing the superconductivity in National Institute of Material Science in Japan, what we call NIMS, and he called me, well, do you have any boron doping samples? And yes, and I sent them, because we are already having the very highly dense, well, the heavily doped diamond, because the semiconductor people like to have a device and what we call P+ layer means the boron-rich regions are very efficiently to get ohmic contact, and also those regions become a source and drain and field effect transistors. So we already have some highly doped layers, and then I sent to one of the collaborators, Dr. Takano in NIMS, and then showed on that day, oh, you had the world record, and oh, that much. So, well, the CBD is a very efficient method to introduce the boron inside. So, yeah. But also at the same time, the French group is a nice work, and they showed the critical, concentrations, okay, on that means how much density of the boron inside, and when the superconductor start. So this is about 5 to the 10 to the 20s. Okay, this both cases shows this is a metal insulator transition takes place in here, but that means the superconductor also correspond. The superconductor transition also the same. Those are French group. And we also have a ungroup-resolved photoelectron spectroscopy with our collaborator, Professor Yokoya. And what we shows that from the balance, this is the balance band structures. And balance band structure top is, it's a plateau, means these orange regions are where the electrons, the valence electrons exist, but it should be like that, but these layers are cut. I mean, that means film level. Sorry, I didn't explain those boron concentration. Sorry, this is a superconductor. It's a 3 times 10 to the 20s. And almost the film level is reached on the top of the valence band. But this is one of the highest concentrations at that time, the 8 times 10 to the 21st, almost 1 times 10 to the 22nd. Then you get the plateau regions, and then the Fermi levels enter into the valence band. So this is one of the evidence why the superconductor takes place. And also this film surface is very important to explain the mechanism of the superconductivity in diamond. So we also repeat the French groups and in a different substrate. Because French group, you normally use the 001 at that time, and we use 111. Because 111 diamond surface, well, this is very efficiently, the boron can be incorporated, and then those temperature become high and high. So the starting transitions, superconductive transitions were almost the same or a bit low, 3 times 10 to the 20s per cubic centimeter, but the TC goes up according to the boron concentrations, and the 001 case is stopped, but 111 just goes high and high. And right now, one of the highest, well, we can reproduce almost the 10 kelvins. It's like that. So this is a resistance of the function of temperature. It's very simply, we can say our case is about 10 kelvin. So and transitions from normal conducting to superconducting transition is very sharp, between 0.1, not 0.1, but 0.5 Kelvin. So this is an enlarged image, but here, oh yes, it's in this case, 0.2 Kelvins change, and to the normal conducting to the superconducting region. So anyway, also we can observe this little bit thin layer. This is not thin from the point of surface science, but of the material science, well, less than 1 micron is very thin, and the mostly successfully or reproducibly observed superconductivity is relatively high temperature, above 10 Kelvin, we get relatively thin material. And also we applied magnetic field and see what happens in the HC2 change. And according to the thickness, and the thin films shows very high magnetic, it's about 15 Tesla, or it's about 15 Tesla. So I think this material is very strong, very resistive to the high magnetic field. And very recent result, we also obtained in ARPS spec in the same group. I think first also is young people, but also we collaborate with the Dr. Yokoya's group. And I think it's relatively sharp, plateau we get in unresolved photoelectron spectroscopy, and the film level really cut, into the valence band. Well, that's what we saw from this spectra. So, okay, this is so in early stage of the superconducting diamond, we started from 2004, and after first paper has been published from Russian, but we are using a CBD, and then we have some contributions for the CBD and polycrystalline diamond. We can get relatively high TC, and then gradually we learn how to make these layers, and many basic research people are going to measure our samples, and some result we could get, and one of them we are going to show you. So, but before that, I just explain again how we make it. So we are producing diamond normally, and we add polymetal boron. I think we don't explain about how to get boron doping, but this is a boron source. How to get boron is this gas phase. And this is a boron is surrounded by 3 methyl bases, and that's polymethyl borons. And some people, yeah. So another, we're firstly using diboron B2H6, but which is very toxic gas. Although polymethyl boron is not so not so friendly gas, but it shows very efficiently introduced into the diamond, and also it's not so toxic as diboron. So that's why we're using polymethyl boron instead of diboron. And also the polymethyl, that means this carbon doesn't affect the materials because the diamond is made of carbon. So some semiconductor people doesn't like carbon incorporate into the, because silicon people doesn't like carbon, but we doesn't matter. So it doesn't matter for us. And the plasma we are making is very efficiently local regions, but this is one of the reasons why we get a little bit high TC compared with other group. And the plasma is very focused on these regions. And this is a microwave plasma. Microwave is, as you know, we use the microwave oven, and the power is just 400 watts. So you know, when we heat your coffee or some other hot dogs or something like that, I think normally we're using 500 watt. So it is lower than that. But then it's concentrate in these regions. For example, this is just 1 centimeter, very small regions, and then the plasma ignited, and then the center plasma is just on the substrate. And so it is very focused regions. We get very high dense plasma. And the pressure that you can see was just several times lower than atmospheric pressure, but it's enough to get superconductivity diamond or nice air. Without boron, of course, we get nice pure diamond, but this machine is good for the doping. So this is another explanations for that of the boron doping effect. You know, the boron is atoms which is larger than carbon, okay, when we make a lattice. So, and then atomic distance, just the calculations, very old properties. We use the Bega's law, which is, I don't know, in the last centuries, you know, theories or just law. But anyway, when we increase the boron concentrations and the perpendicular lattice expansion we observe by X-ray measurement, and then we get the lattice expansion is very clearly thin, and we can get the 0.5% lattice expansions according to the boron concentrations. and also TC is high in these regions, and then we get very high expansion in particle. But okay, oh, this is a big another one, and these expansions, according to the Boron concentrations, there are some tendencies, and some case the substitution site cannot be occupied only interstitial site. In diamond has a structure has a very large regions for the interstitial site. So the impurity is easy to be incorporated also in the interstitial site. And if we prohibit or how more very efficiently we introduce the boron, then only substitution site. So this is the one we get in some conditions where we get high TC. So this is very simply we can explain how we get high TCs, how we get the substitutional site boron. Okay, so this is very simple ideas, but it works. So without prohibiting, without to control the interstitial site, but if we can make a substitutional site, then we get better quality of the diamond. And this is one very interesting, pictures, because also we can get carrier concentration as a function of the boron concentration. So this is dotted line, so this is the 1-to-1. Okay, so that means this is 10 to the 21st, and this is 10 to the 21st per cubic centimeter. And it correspond, these lines is the carrier concentrations the same as the boron concentration. Okay, so this is the acceptor boron. So then these lines must be here, but what we measured is a little bit high. Wow, what did that mean? Does it mean? So, or artifact, or we don't know, but this is very reproducibly observed when the TC is high regions, and so we can explain this is a very anisotropical carrier formations, and also we have calculated, and also some other people calculated the film surface is changed to the sphere, to a little bit anisotropic structures. And, the film surface, it is a K-space. So this surface, this is a two-dimensional, but this is the real thing, the three-dimensional. So, and these regions, the holes is very heavy. And these regions are a little bit light. And but anyway, this anisotropic effect shows very interesting phenomena, and sometimes the carrier is also high. It's not only diamond, but other materials. So those things are anticipated or expected. So this is a very interesting, experimental data. So this is a very degenerated structures. So the film surface, we showed ARPAS spectroscopy that the valence band so the film label enter into the valence band and then get these filmy surface. But this is also very anisotropic. It's not.
May I ask a question? You said.
Yes, please. Yes.
So I'm very interested in the process of annealing, and you have not talked about it. All this
annealing.
How do these borons sit in places? Is it really also depending on a processing afterwards, or did you investigate this? Like
well, we are not. Okay, thank you for questions. So we don't anneal, but just I didn't show you the temperature. Sorry, the temperature, gloss temperature is 800 or more. So it is not ion implantation, because annealing normally we use ion implantations, but this impurity is just glowing during the glows of the diamond. some site occupied by this impurity. So then,
because of the high temperature, say you don't need this because the
oh
growth
yeah, yeah,
process
yeah.
is already at high
But this,
temperature and it
yeah,
does the annealing itself, so to say.
yeah, it's
See,
automatically
thank you.
annealed during the growth. And this choice of this temperature, this is know-how, but of course it depends on the operators, but we optimize the temperature and the power of the plasma, then we get the better, okay,
Yeah, I see.
substitutional case, I think.
Yeah.
And another case, well, if you want to try, then I think I'll tell you that but the plasma also very important. So, this is a very know-how things, but sorry, what I'm doing. The microwave we're using is not continuous. Okay. Later, if after my conclusions, so I put some figures to explain our plasma is a little bit different because the microwave generators shows we are using pulse mode. Very classical, microwave generator have a pulse because we are using magnetrons and we using magnetrons shows in microwave wave, like with the oscillation start, but it is in high voltage. So this high voltage and low voltage regions and high voltage regions in like a 50 hertz or 100 hertz frequency. So we are using 50 hertz in Japan, and I don't know what German is, but anyway, and this is and the rectifying we used we using so total pulse is 100 hertz, okay, and then above some voltage, then the magneton start to oscillate, and the microwave start to glow. So this is the pulse in a 100 hertz, and so during between the oscillations, microwave oscillations, then or the microwave generations, then there's no plasma regions. Okay, so I think this is maybe one of the very high, incorporation of the boron takes place in our case. So these are very, very complicated things, but so other people cannot reproduce our result is that maybe this special, but not special, but this very classical generators we're using, and then this is one of the explanations how we get the high concentration of boron. So,
thank you very much. Thank you.
Yeah. So anyway, also what interesting is that these are critical temperatures, TC, and also as a function of boron, and we put some theoretical groups result. So this black one is Max Planck Institute, the Boeli and OK Anderson's groups, and I think it's more than 20 years ago, or nearly 20 years ago, but what they put like that, and this is a Chinese group, and this is Marvin Cohen's group in UC Berkeley, I think, and then also he was very interested in. But anyway, those plots are here. So what we obtain in lead, this work is a little bit old work. This not this year, and it's also several years ago. So some case we are having a plot above the theoretical expectations. Unfortunately, we cannot dope diamond above 5%, or so if we reach the 10%, maybe things are a bit changed, but this is one of the maximum concentration we achieve. So yeah, but we stop here anyway. So maybe more high temperature. So recently, not so recent, but a few years ago, the University of North Carolina I think this is Narayan's, Professor Narayan's group shows very interesting result. This is a composite of the boron and the carbon. So it is beyond, well, which is not diamond, but this composite, they shows in the ratio of the carbon and boron, but maybe this is in the more than 10% regions, and they show the 30 kelvins. Yeah, but not so many papers they published, and only few papers. So nobody could reach, nobody can reproduce. So unfortunately, but I think the carbon boron makes something interesting.
Professor Kawarada, a quick question.
Yes, please.
Could the pressure help a bit?
Yes, the pressure is very important. Even the plasma pressure.
No. If you have already some concentration, some sample, would the critical temperature change when you increase the pressure? For example, in an anvil or something.
So what I mean pressure is, well, we have a uniaxial stress, and also we have high pressure experiment. I'm not so specialized in high pressure experiment, but someone pushed the diamond, okay,
yeah,
during the high pressure, but I think gigapascal or something like that.
Yeah, that's right.
And then, okay, so then they showed very clear tendency. I'm sorry, I don't have this bibliograph today, but the diamond, what we observed is relatively expanded in vertical. I think there's the data for that. If you're, well, this one, so I mean, this is a reciprocal mapping of the X-ray, and I'm sorry to say, and this is a substrate, this is a layer film. So this is a reciprocal mapping, means a reciprocal lattice measurement, and this is a one planar structure. This is a vertical. So in the vertical, the reciprocal lattice becomes small. What that means, okay, this is a schematic biography. It's easy to understand what's happening. So you can see the lattice expand like that, in vertically. Then we get relatively high TC. So our collaborators in Osaka University and Professor Shimizu, I think he's very specialized in the high pressure measurement of the superconductivity. And he pushed, it's like one uniaxial stress, and then the TC goes down, okay?
Down,
but that means the down, because so this is the one, so this is the expansion is one of the reasons in the thin film, we get relatively high TC compared with the relaxed, lattice. Right? Relaxed means that it's not vertically strained, but it's a relaxed case. So these relaxed layers are not so high TC. So I think this is strain is a yes, uniaxial strains caused a little bit large TC. So it affects, of course, in the electric band structure. And I'm sorry we stay, but still we are not calculating things like that. But I think the uniaxial stress changed the valence band structures, and then heavy hole, light hole balance changed, and so that caused such a relatively high TC, I think. So sorry for a long answer, but I think the pressure is very important measurement to see what happened in our superconductivity. So is that okay for that?
Yes, thank you so much. We have people here at Mainz who are doing high pressure superconductivity.
Oh, really?
Yeah. Professor.
Oh, yeah, high pressure. Okay.
Yeah, Professor Eremets. in the Max Planck Institute for Chemistry. So that's why.
Oh, yes. Yeah, I know the high pressure region, but I'm not so special in the high pressure superconductivity, but well, they are almost the room temperature, things like that. Right?
Exactly.
So,
Yes. Yes.
yeah,
Yes.
so, yes.
Yes.
Very interesting,
Yeah.
yes.
He actually measured also the superconductivity properties in boron under high pressure.
Anna, your microphone is not working properly.
Sorry, and thank you. I just said that, well, I was also Googling a bit around, and there is a paper by Michael Eremets about superconductivity in boron from 20 years ago as well. So under high pressure as well. So, I posted it in the chat. It's just...
sorry, I cannot hear you.
Is my microphone better now? I mean, I changed the microphone.
It's good quality, but very quiet.
I'm sorry.
I become old, so my ears not enough.
No, I'm just quiet.
So
I just said that I had a quick Google search on boron because on boron superconductivity, and then Michael Eremets here from Mainz popped up, and he studied the superconducting properties of boron beginning of 2000 and under high pressure. Right? So
okay.
And I posted it in the chat, the paper, just for your information. Because I thought there's so much boron already in your diamond, I was interested in what are the properties of boron actually as a superconductor.
Okay, so in our case, so people already also very at the initial stage of this superconductivity, and the boron carbide, its segregations or boron itself become, as you know, the boron itself becomes superconductivity. So these possibilities also checked, and but CBD is relatively homogeneously boron can be, incorporated compared with the high pressure technique. The first Russian group is very nice result they made, but also their material, the boron carbide phase or boron rich, very rich phase coexist. So, but CBD is relatively simple. Yeah, so but these layers cannot be observed. So what that means, I think, in our case, it's very simple. It's semiconductor-like superconductive. Semiconductor means like a silicon, the boron incorporations, and then it shows superconductivity in the substitution side. So just quickly overview what's happening in the thickness measurement. Sorry, the thickness difference of our material is that this is a cross-sectional TM, and the TM substrate. Sorry, TM specimens are not so good in this case, but anyway, this is relatively homogeneous, and then we get the defect a little bit far from the interface. And then finally, we can clearly, this is a thicker, relatively thicker film, like 900 nanometer. And you can see this location start, this is not this, I think starting poles start from the interface, but mostly in the middle in this case. And this is a very fancy bugleups with a 4-micron thickness. And you can see this is the layers are relatively defect free. And then some thickness, like 500 or less, 400 to, that's what we observed in the thinner films. These, 200 nanometers or that much regions, then this defect start. So this is we call misfit dislocations, but later with not misfit dislocation, but the starting fault is mostly easily to be explained. So the superconductivity it's going these lesions, I think. So the thin lesions. So what difference between this defect lesion and the non-defective lesion is that, well, this lesion is stress is already, or it's not relaxed, sorry. So yeah, this is a schematic view to summarize what's happening. And anyway, the strain layers we have here, this is a strain layer. So these strain layers are very influential for the high TC in our case. So we changed the boron concentrations, and we see the critical thickness concept. Critical thickness is where there's the thickness when the strain layer become relaxed. So normally this concept is, well, this concept is studied by silicon or silicon germanium. And the people being this group, I think this group used to be in Bell Lab in 1980s or 1990s. And this group shows a very nice result in silicon germanium compounds, and they see how much, critical concentrations, critical thickness is observed by TM or X-rays. So we borrowed these ideas, and also the theory of thickness and large mismatch. We plotted many samples, and also there's error bars are large. But anyway, we are nearly these lines where the people beings, that means the group suggested in 1980s or 1990s in silicon and silicon germanium case. So because do you know the silicon germanium and the diamond is same crystal structures. So I think this kind of this models can, explain our critical thickness. So anyway, that's much we changed is the boron concentration high. Then we get from the X-ray measurement nearly 0.7%. That's much we observed from the kind of this measurement in reciprocal mapping. So yeah, that's, and I think, we don't have any good collaborators to calculate those valence band effect on the stress or strain. But I think this can help the high TC, relatively high TC in 10 Kelvin. It's not high TC, but compared with other groups, we get high TC, and then these strains measurement and also calculations helps us. Okay, so I just summarize other materials in the doping concentrations at the TC and what we have in diamond. You can see those diamond placed like that, 10 to the 20s. Second, and then these regions, and other like a boron doped silicon or boron doped germanium. Or recently, boron doped silicon carbide shows superconductivity. This is a French group, and the same group that did in diamond, but they showed nice result in silicon or germanium, I think. And one interesting is that the optimum concentration of the impurities are in these regions in diamond. And some SDO also shows superconductivity, but the optimum ratio is relatively low. And then metallic phase also, or the non-superconducting phase appeared after heavy doped regions. And we don't know what's happening because this is still in a nearly, this is 10%, but beyond that, what happened, we want to study. But now we summarize this result compared with other materials. Anyway, the above superconducting regions relatively wide range. So, okay, so maybe the time is already over, but we will just explain what's happening in our device. And then before that, we measure the superconducting gap, which is not published yet, but it's interesting. And also we measure the superconducting gap using IV characteristic, and the gap we get is about 1.3 millivolt, which is also expected from scattering autonomous spectroscopy by other group, but the sample is our sample. So they measured 0.9 or 0.87 milli eV, and which is almost the same. But this is just simple measurement using aluminum oxide and aluminum probe. And but this is very reliable, or very easy to measure from the IV characteristic to get the superconducting gap. This one is more sophisticated measurement, but anyway, almost the same. But this is very focused in the very surface areas, and we are also including not only surface area, but little bulk properties that we get. I think this is a little bit complicated. So also we measured some anisotropic upper critical field where the superconducting stop. So on the horizontal magnetic field and the vertical magnetic field that you can see when we change the magnetic field, and then TC goes down, and because this is TC, well, transition temperatures goes down, but this tendency you can see the vertical magnetic field and the horizontal magnetic field, they're different. So we call this is anisotropy takes place, I think, and then we measured vertical and the horizontal, well, magnetic field, and then we see the different HC2 point here and here. So then we using this plot, and then in a thin film, less than 20 nanometers, we plotted HC2 like this. So in this case, there are the two models to explain these tendencies, because this is the angle for the magnetic field that we applied, and then we can see this shape. So this shape corresponds to the 2D Tinker model compared with the 3D Ginskell-Palander model. And this is coherence length, and this is thickness, and the coherence length is might be above the, but this is not so easy to explain. But anyway, this is a very difficult conditions to explain, because our coherent length is not as big as a 20 nanometer, I think. But this case, it clearly shows the 2D Tinker model can be applied. Unfortunately, this result has been rejected by the some journals. So we try and to get better explanations to be accepted. But anyway, this is very interesting. 2D models can be applied. So this is a little bit new data. And okay, and also junction. Yeah, Josephson junctions we measured, and to make Josephson junctions, we used many ways, because I think if you know how to make Josephson junction, there are a lot of ways, and to make microbridge structures or bicrystals interface or grain boundaries and barriers, many ways. And we are firstly using microbridge, but it's not so successful, and then grain boundaries or bicrystal structures are very, we will also want to do, but right now we are making steps to get the crystal grain boundaries or some discontinuous regions to get SQUID, sorry, Josephson junctions and SQUID. So are we making a step like that, or some trench or some steps? And well, you can see during near the steps, then the inhomogeneous or very discontinuous layers appeared, and then this is in the bottom, this is a diamond layers, and this is a bared substrate. The substrate is also diamond, but this is heavily doped regions are a little bit dark image, but this is the SEM image, so I don't know why it we've gone dark, but anyway, here in the bit, this is not surface, but a little bit near the interface regions, there are weaklings takes place, and then Josephson junction would be made. Also, the same thing is true in this case. The surface is a little bit defective, but it doesn't matter. Then we can get the Josephson junctions and the Shapiro steps, which is one of the evidence of the Josephson junction is clearly thin in these trench or step regions. And this is a cross-sectional TM, and unfortunately, this is very defective in the surface areas. But I think supposed to be here, we could get the weaklings somewhere else in here. And the one of the most important IV characteristic, resistance and temperature relationship is we have a two-phase. Two-phase means TC 10 kelvins regions and relatively low temperature regions. In this case, it's 8 Kelvin, for example. So the two-step transitions takes place, and which is evidence for the Josephson junctions. So these regions or junction regions are relatively low TC, and it's these far from junctions. We just show the 10 Kelvin, this normal case in our film. So these two regions, these regions we get Josephson junction. And another case is here. Also, we could get relatively, this is a logarithmic scale, so you can see these regions are also another TC regions, and it's not clear in this one, but also the junction takes place in here. So in two cases, we just measure the IV characteristic as a function of the temperature, and then we of course measure the ICRN, which is one of the parameters to evaluate we get how much Josephson junction we get. So one other case is relatively high temperature Josephson junction we get here, and relatively high ICRN, which is relatively higher than former. It's the same. Okay, that's a change for this one. Anyway, we make small junctions. Then we want to make better SQUID structures. So in this case, also we get Josephson junctions, and I think the result was not so different. What was different from here and here? Okay. Yeah. Then we moved to SQUID, and we were forming the SQUID structures by using two parallel Josephson junctions. And before that, our work, the pioneers making SQUID using a non-crystalline diamond. Non-crystalline diamond is a diamond, but it has small crystals. And then it shows very nice SQUID, even if temperature is low, but this first time they published, this is ACS Nano, they published in 2011. And these Josephson junctions they made for the SQUID is a lot of by the crystal boundaries are there. There are many boundaries, I think. So we don't know where the Josephson junction is. It's multiple junctions, and then, but anyway, they show the really good SQUID. You can see the oscillations here as a function of the magnetic field. And in our case, to the case that we just show, but we just tried error, then we make a literally reproducible one again and again. And I think both structures that we used in Josephson junction, we use for the SQUID structures. And I think this is a little bit. Also, we want to get is the small lines of the boron doped layers to get the small junction. This is a relatively large junctions that we obtained. This is the 30 microns, so that much we showed before, I think. Okay. Oh yes, 30 microns, so 50 microns, but now we want to approach micron or submicron regions. And to get this, we should make a very narrow boron doped layer. And we use selective gloss or etching. So the selective gloss is also been made. We make some mask, metal mask, and then we get the boron doped layers, which shows, well, this case is 500 nanometer, that's the submicron regions we get. Another case is to make etching, but etching is better because selective gloss, as you can see, this is edge part is become like overhang structures here on here. And these layers are non-superconducting regions. And then we are not getting better quality of the junctions, Josephson junction. So that means we cannot make a SQUID from this is looks like good, but not for device. So I think we need a more skillful technique to get the narrow devices. And yeah, we checked the line width effect on the TC. So the line width means this one here, and the low line width, we get the low temperature, the low TC, and this is maybe caused by the we cannot get homogeneous, current flow in this case, and we are making very narrow devices anyway. So, and this is not so narrow junctions. I think this is SQUID oscillations in relatively large one, as we showed in SQUID, sorry, as in this Josephson junctions at the same. And we get this kind of oscillations. And I think just as I think it's times. Okay, so I think this is one of the best one, which can we can show you that was kind of this oscillations very nicely observed, and the period, this is the 2 micro Tesla, and I think the lines we obtained here is 5 microns. So this is the minimum junction width that we approach to get SQUID oscillations. So we are approaching narrow anyway, SQUID, and to get qubit structures, for example, using this type of SQUID. Then we are going to try another point of view. And anyway, with from the SQUID, we get peak to peak. That means here, okay, here to here, the peak to peak. About 40 or 50 microvolt we get. This is relatively low temperatures, but it's okay. And of course, compared with other SQUID and the commercially available one is, of course, this value is much higher than others, but now we are approaching using narrow stripe patterns. And finally, what we are going to next is to make to use our specialties, because we are making transistor structures always for the FET, but not only for FET, but this is superconducting field effect transistor we are approaching. So we are making type of this structure already, not for superconducting device, but just the high frequency transistors. So we produce the P plus layers, and here selective Boron, and here is undoped layers. So we get two-dimensional whole gas in here, and then we make devices, and this works very well from the point of field effect transistor. So this is the IB characteristic of the transistors. And this is the current density we achieved, one of the best in diamond. And this is not as good as gallium nitride, but better than silicon carbide. So this is one of the good values in wide band gap material. So anyway, what we want to see from here is that this two-dimensional whole gas is only we have chance for the current we obtained. So normally in the superconducting and non-superconducting junctions, what we obtain is, maybe do you already know? Okay. Proximity effect, or if there is a superconducting, here is a non-superconducting regions, the under diffractions here we obtained, but this case is only hole is we get, because diamond we cannot expect current, we can expect electrons for the conductions. So it's a wide band gap and the low temperature, because so these regions, even if the here superconducting regions and then Cooper pair enter into here, but it still keep, I hope. And in a non-superconducting regions, then electron holes coexist, and then if hole enter, then the electrons recombine, and then Cooper pairs could be destroyed or decomposed. But here, its only possibility is a hole. So if we can get controlled superconducting device could be achieved, well, I think this is a very interesting device, I hope. So this is one of them, sorry, okay. This is the closing announcement for the Japanese. And okay, thank you for interest. That's all.
Oh, thanks a lot for this quite great overview over what you can do with diamonds. I'm sure, I mean, we had a couple of questions during the talk, but maybe there are other questions.
Yeah, indeed.
Dima.
Thanks for very much for the talk. There was some interesting discussion that if diamonds superconducting junctions become available, and also diamond, so you asked about our interest. So I think there are some people here in the audience, including our group, who are working with nitrogen vacancy centers in diamond as sensors. So and those have been considered as an architecture, for instance, for quantum information. And if you have both superconductors and NV centers together on one chip, one can think of very interesting combinations of, for instance, information processing and storage and so on at the same time. Can you comment on these prospects?
Well, that's great. Well, I cannot make a, precise answer. I think we are just doing the NV Center, but still my NV Center work and Diamond superconductor work is not collaborative. So one collaboration we can expect is, you were using NV Center as a storage, and Diamond superconductor is, of course, some qubit calculations or even aluminum, and but Diamond is, we can get similar approach to get superconductor operators or something like that. Then we get a nice combination. In all Diamond device could be made. But yeah, but I think this kind of approach, the aluminum is, we studied aluminum superconductor and device because the coherence length is very large. And so this is very advantageous. So, well, there's another work using aluminum superconducting qubit and then Diamond NV Center for the storage. Well, this combination is not bad. Well, of course, we want to hope the Diamond superconductor, but so that's why we are approaching the SQUID right now, but it's not for qubit, but for some other application like SQUID microscopy, because SQUID, you know, the AFM tip, very recent AFM tip is made of Boron doped diamond.
Yes.
And yeah, but I think conductivity is not good enough compared with others. So. But anyway, and these combinations are made with the SQUID microscopy is not so unrealistic. So I think this is one of the application right now. But if we can make a Joe FET or some other Josephson FET or Josephson Junction FET or some other superconducting FET, which has a large, was not coherent length is not large, but if the proximity effect is within our controllable regions, because we're approaching very close, very small devices we are approaching. And then in that case, well, we combine with NV Center to make something interesting device that we can achieve. So the NV Center is because there's a storage device or sensing device and more Diamond device. This device can make something more calculating part or operating part, but I'm not so sure. So yeah.
May I ask one more thing real quick?
Yes,
Anna?
please.
Yeah. Okay. So our group has been interested also in using NV centers to measure superconductors. I just posted the review paper reference in the chat there, and in particular we've been using wide field imaging to look at high temperature superconductors, and we always wanted to look potentially at the diamond superconductors, but we were never able to get hold of a good sample. So
okay, doesn't matter. Yeah, I can send you. Yes.
This would be fantastic. So we are not really equipped to go to very low temperatures, so but near 10 Kelvin should be really fantastic.
Okay, yeah.
Would be super interested in looking at that, if possible.
Yeah, please. Yes. This is one of the great chance to collaborate, and also, yeah, that's the discussion will be fruitful, I think, and yeah. So, yeah, keep in touch.
Okay, well, we'll send you an email. Thank you so much.
Yes,
Thank you.
yes,
Fantastic.
Yeah. This is der große Gelegenheit zusammengearbeitet. So, ja, zusammenarbeiten. So, yeah.
Okay.
Very
Das
good.
ist ausgezeichnet. Vielen Dank.
Yeah.
Oh wow, yeah. Thanks a lot for this questions. I would like to announce who's speaking, giving us the last quantum seminar of this semester next week. It's Professor Stefan Philipp from the Walter Meissner Institute, and he's talking about controlling superconducting quantum circuits for quantum information processing. So at least a bit in the same direction as we heard today. Is there another urgent question, or? I mean, most people have already left. I mean, this is normally the time that we also end the seminar. So
yes. Okay.
and it's also pretty late in Japan, right? So
10:30. Okay,
10:30, yeah. So well, thanks a lot for the super interesting talk. It was a pleasure to have you here, and yeah, let's keep in touch about sending you us our diamond samples.
Yeah, I'm writing an email now.
Okay, thank you.
Thank you so much.
Yeah.
Thanks a lot. Take care, everybody. Bye.
So,
Bye-bye.
yeah.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Schönen Abend.
Okay.
Tschüss.